Okay. Hello everyone and welcome to today's lecture. So in last lecture we were talking about process synchronization and what had we covered? Yeah, if I yeah, we started talking about semaphores, and before that we covered spin locks and atomic instructions like test and set and compare and swap. And then we discussed spin locks. The problem was spin lock was the busy waiting, a process which is not able to get a lock, continuously keeps checking the lock again and again, which wastes the CPU time. So then we said, okay, can we have a mechanism where a process which fails to get the lock doesn't waste the CPU time, but actually is suspended or blocked. And for that, we said that yes, we can use actually the idea of semaphores. And then we had we categorized semaphores into two categories. One is the binary semaphore, and the second one is the counting semaphore, right? So we will actually start our discussion again, but first couple of slides I will go through them quickly because uh, I just want to how to say I just have a animation to make it and explain and to make it clear to you how semaphores work, but some other slides they are same which we have seen the last time. So semaphores, these are the synchronization tools which does not require the busy waiting, so they are different from spin locks. So in semaphore, what we do is that we have it. Semaphore is basically simply an integer variable, and with each semaphore we have an associated wait queue. So there are two standard operations which are performed on a semaphore. One is wait operation, and the other one is the signal. Besides wait and signal, you also need to initialize a semaphore. So then once initialized, you can access a semaphore only by calling the wait and the signal operation on a semaphore and no other way. And both of these two operations are atomic, which mean that a thread or a process which is performing the wait operation cannot be interrupted in between when the wait operation is in progress. And same is true for the signal, which mean that kernel actually implements it by using the atomic instructions. So what is meaning of semantics of these operations, wait and signal? So the semantic are the like the operation, how wait operation works. The detail of this operation are shown here. Again, it is not how it is implemented, it is just how it works, right? So when you call wait operation on a semaphore, the value of that semaphore, the integer value of that semaphore is decremented by one. And after that, after decrementing, if the value becomes less than zero, then the process adds itself to the list of the processes which are blocked on that semaphore, right? On the other hand, the signal operation, whenever a thread or process calls signal on a semaphore, the value of the integer value of that semaphore is incremented by one. And after incrementing, if the value is still less than zero, then a process is removed from the list of the block processes, and it starts running. Okay, so not actually start running, but it is put in the ready queue, and then the scheduler schedules it depending upon the scheduling algorithm for execution, right? So let's say that we have initially a semaphore. We have a semaphore whose integer value is set equal to 3. So actually in this slide, we don't have the definition for for defining the structure of the semaphore type, but you can consider it just like a structure which has two variables, two data members, one. So let's say I'm saying semaphore S. So it has two members. One is the value. I'm writing only V for that, and other is a list, which is actually simply a pointer. and it points to the list of the processes which are blocked on that semaphore, or which are waiting for that semaphore. And when are they blocked? The a process is blocked whenever it calls the wait operation on the semaphore, and after decrementing the value of the v becomes less than 0, right? So let's say we have a semaphore whose integer value v is equal to 3. I'm just writing s for that, not v. So initially, as we initialize the value of the semaphore equal to 3, and then let's say a process P0 invokes a wait operation on the s. So if the wait operation is invoked, now what will happen according to this algorithm? That s is first decremented, right? So it becomes 2. The value of the integer is decremented by 1, so it becomes 2. And then after that, we check if the value is less than 0, then the calling process will be put to the list of the waiting processes, or added to the list of the waiting processes. But the value is not less than 0, so P0 will not be suspended and it will continue to run, right? So if like it was less than 0, then it will not be able to continue its execution, right? Now let's say after that another process P1 executes the wait on the same semaphore, right? So what will happen? The value will be decremented again. So this time it will become 1, and again it will be tested against 0. Since still it is not less than 0, then P1 will not be blocked, or it will not be put to sleep. It will again continue running. Then let's say there is another process P2, which again calls the wait, right? Or wait on the same semaphore, and the value is decremented again. And the decremented value is not less than 0. So the process is not put to sleep and it still continues work. It continues its execution. Now let's say there is another process P3 which invokes wait on the same semaphore. This time again, s is decremented and it becomes -1. Now, since the value is less than 0, so this process P3 will be blocked, which means that it will not be running anymore. So it will be put in the list of the it will be put in the waiting queue. It will be blocked, so it will not be running anymore and will be placed in the waiting queue or wait queue, right? If another process P4 executes wait again on the S, so uh, what will happen is that again the value of the S will be decremented. So this time it will become -2, which is again less than 0. So which means that P4 will be now blocked, and it will also be placed in the wait queue. Now let's assume that the P1 which was running, it is done. During its execution, it invokes signal on operation on the semaphore S. Now when the signal operation is invoked, the value is incremented, right? The value of the integer is incremented. So it is -2 currently. After incrementing, it will become -1, but it is not still less than 0. So uh, since it is not less than 0, then mm, yeah, the value is not less than 0, so remove a process. So we should yeah, so sorry, so the value is less than 0,
-1 is
so what
still
will
less
happen?
than, so
Yeah, I am reading it in the opposite direction. So since the value is less than 0, actually here it is well, almost midnight, like 30 minutes to midnight. So that's why I
oh
think my
no.
brain is starting working now. So anyway, so since it is less than 0, the P3 will be removed from the list of the block processes, and it will be it will continue with its execution. Assuming that actually when it is removed from the waiting queue, it is put in the ready queue, and then the scheduler will, according to the scheduling algorithm, will schedule it for the execution. But it will move to the ready queue, right? So that's why it is now removed. And now we are assuming that P3 is running. So we are assuming that it is immediately scheduled for execution, right? And again, if let's say the P0 which was running during its execution, it invokes signal on S. So what will happen is that S will be again incremented by 1, and its value will become 0. And then since its value is less than or equal to 0, this condition is true. So it's mean that the P4 which was waiting or which was blocked on the on that semaphore, it will be unblocked, and now it can start execution, right? So one thing which you which you need to keep in mind, like if the value of the semaphore is negative, so it basically tells you that how many the magnitude of that value tells you that how many processes are currently blocked on that semaphore, are waiting for that semaphore to be signaled, right? So when it is -1, it's mean that one process is waiting or one process is blocked on that semaphore, and if it is -2, so we had two processes waiting for that semaphore to be signaled. So the wait and the signal operations which we have seen, again, as I said, this is only the code to explain the working of the semantic of the wait and signal operation. This is not the way how you implement it, because remember, the implementation of wait and signal needs to be atomic. Atomic mean like if let's say a process is executing wait, so it should not be interrupt when it is executing it is in the middle of performing the wait operation. But again, even if we look at this higher level language statement, there are multiple statements, and when I will translate them into assembly, there will be more instructions. And you know that any thread or a process can be interrupted, or it can be context switched between any two instructions within its code, right? So the wait body and the signal body, they have to be executed atomically. So one process at a time. It's mean that only one process can execute the wait operation or the signal operation on a semaphore at a given time. So which mean that signal and the signal and the wait operations, they are treated as the critical section to be protected by the kernel. So which mean that only, since we are saying that no, again, let's say you have process A and process B, and both want to execute wait, right? So as we said, wait and signal both need to be atomic, but let's say both A and B want to execute wait at the same time. So in order to provide the guarantee that only one of them can execute wait at a time, it's mean we need to treat wait of the implementation of wait, or the code which is implementing the wait, as a critical section. Only one process can enter into this critical section, either A or B. Similarly, we don't want two processes to execute the signal operation at the same time. So which means that signal operation, the code implementing the signal, should also be implemented as a critical section. Semaphores, last time we mentioned that semaphores are of two types. So one which can have the integer, in which the integer value can have the range of only 0 and 1. Uh, and they are very similar to mutex locks. Actually they are the mutex locks, not similar. They are same as the locks. Uh, they provide the mutual exclusion. Uh, Continuing semaphore, these are the semaphores which can have the integer value can have a range, any range greater than equal to 0. So we will see how in different situations both type of semaphores can be used. So one use case for the binary semaphore is where you want to protect the critical section, or you want to enforce the mutual exclusion. So binary semaphores, which are also known as mutexes, they can be used to solve the critical section problem. So what we do is that we share a semaphore or a mutex among n processes, which and such that only one of them can enter the critical section at any given time. And again, since it is a binary semaphore, so we initialize the integer value to 1, and 1 is the maximum value. I mean, it can have only two possible values, 0 or 1. So if we use the mutex to solve the mutual exclusion, to achieve the mutual exclusion, so this is how our code of the program should look like. So before entering the critical section, you invoke a wait operation on the mutex, which is basically a binary semaphore and nothing else. And once you are done with the critical section, you invoke the signal operation on the mutex. So now let's say that we have two processes, process zero and process one, and both share a critical section, which means that only one of them can execute the critical section at any given time, or only one of them can enter the critical section at a given time. And this is, as we said, this is how their code should be organized. Before the critical section, you should have the mutex, wait operation on the mutex, and after the critical section, you should call signal operation on the mutex, right? So now if we have the mutex value set equal to, let's say, I'm just putting the v for its integer value, if it is initially equal to 1, now uh, if you invoke wait on mutex, so what will happen is, like, if only, again, remember we said that wait itself is the body of the wait itself is a critical section, right? Let me go back here. Wait body and signal body have to be executed atomically. So one process at a time. Hence, the body of wait and signal are critical sections. So they themselves are critical sections. So here we are not in this code snippet. We are not looking at the internal code or the body of the wait and the signal, but they should also be treated as critical section, right? So which means that only, let's say, process 0 or process 1 can perform the wait operation. Both cannot perform the wait operation at the same time, right? So if process 0 is allowed to perform the wait operation, so it's mean that it is able to enter its critical section, and process 1 will be waiting. So process 1 will be then able to enter the critical section only after process 0 has performed the signal operation on the mutex, right? So what will happen, like, let's say if we have this sequence. Let me discard the. So what will happen? Let's say if we have this sequence that process 0 first invokes the uh, process 0 first invokes the wait on the mutex. So what will happen is that it will able to continue its execution. Why? Because the value of integer is initialized to 1. So when you invoke wait on it, the value is decremented by 0, but the decremented by 1 and becomes 0, but it is not less than 0. Since it is not less than 0, so here you can see, uh, since it is not less than 0, that's why the calling process is not blocked. So the calling process is not blocked, and it continues its execution, which means that it's entered the critical section, right? But let's say if process 0 is in the critical section, or at the same time when P0 wanted to execute wait, P1 also wanted to execute wait, but only one of them can do that. So when P1 will execute wait, so what will happen? That the value of integer is 0, so it will be decremented by 1, so it will become -1. So since it is less than 0, so process 1 will be blocked. So it will not be able to uh, continue. It will be put in the list of the waiting processes. Does anyone of you have a question? No? Okay. Uh, so it will be blocked. And now how long it will be blocked? Until the process 0 is done with its critical section, and then it reaches the point where it invokes the signal, performs the signal operation on the mutex. So now when it will perform the signal operation on the mutex, so what will happen is, like, your value of the integer is incremented by 1, so it becomes 0. And then according to the definition of the signal, if the value is less than or equal to 0, one process will be unblocked, right? So this process which was blocked, P1, it will be unblocked, and it will be able to enter its critical section. Yeah.
That
Uh,
seems pretty clear. Yeah.
yeah. So in this way, you will be able to achieve the mutual exclusion using binary semaphore or mutex. Again, wait and signal. These are the system calls which are implemented by the kernel. Again, it is the responsibility of the kernel to make sure that weight and signal are implemented in an atomic way, which means that only one of the processes, process 0 or process 1, can perform the weight or a signal at any given time. So it is not possible for more than one process to execute weight on the same semaphore at the same time. Also, semaphore mutex, it is also a kernel level variable, which means that user level code cannot directly manipulate or change its values. So its value can be changed only through wait or signal operation, which are again the kernel level code or system calls. Okay, another usage where we can use another example where we can use the semaphores for synchronization is, let's say you have two processes P0 and P1, and in its body the P0 has some statement S1 and P1 has some statement S2, and our requirement is that we definitely want to have S1 executed before S2, right? So you can achieve that, or you can enforce that ordering by using a semaphore. So let's say initially if you have a semaphore X and you initialize and its value is initialized to 0, and then what you can do is that you can make P1 to wait on X before executing S2. So if now X is initialized to 0 and P1 wants to execute, if P1 executes wait on X, so X will be decremented and will become -1. Since it is -1, P1 will be blocked, right? And now it will be blocked, it will remain blocked as long as there is someone else performs a signal operation on X and it increments the value back to 0, right? And then what we can do is that we can make P0 to perform signal operation on X after executing S1. So after executing S1, if it performs signal operation on X, so it will be the value of the X will be incremented to 0, and which will actually unblock P1. So we are forcing the order that S1 will always be executed, because after S1, the signal will unblock the process P1 and then it will execute S2, right? Okay. Uh, Here is another example of using semaphores to synchronize producer-consumer problem. We have seen this producer-consumer problem earlier, like at least two times before, in different, like one case where we are using the buffer size, but we were using the buffer, but we were not filling all the slots of the buffer. Then we had a look at the other example where we wanted to use the locks so that we can use all the slots in the buffer. This time we are going to use semaphores to synchronize, not locks, not spin locks actually. We are going to use the semaphores to synchronize producer and consumer. Here, what we are assuming is that we have a buffer. Buffer is an array of buff size, and it can contain at most buff size number of items. So here, on the producer sides, what we are doing is that when you produce an item, after producing, you check if the count is equal to buffer size. Again, count is a variable which indicate that how many items have been placed in the buffer. So every time we place an item, we increment the count, and every time we remove or retrieve an item from the buffer, we reduce the count by 1. Okay. So before putting the item in the buffer, the producer checks that is count equal to buffer size. If it is, it simply waits, because it will be like stuck in this while loop, right? But if count is not equal to buffer size, it places the newly produced item in the buffer at index n. If you remember from our previous example about producer and consumer, so n is the index where you place the new element in the buffer, and out is the index from where the consumer picks an element from the buffer, right? So it places the element in the buffer at the location or index in, and then it increments the index by 1, and then you take a remainder with buffer size, because it is a circular buffer. So if, let's say, in the buffer you have 5 elements, so the index will be incremented from 0 to 1, then to 2, then to 3, and then to 4, and then from 4 it will be reduced back to 0, and then 1, 2, and 3, 4, 0, so on. So anyway, so after that you increment the count. And at the end, you signal the full cells. Full cells is what? Full cells is actually a semaphore, right? So let's say I am only writing FC for full cells, right? So if the buffer of the let's say the size of the buffer is 5, so we initialize the semaphore integer value with the value of sorry, we initialize it with the value of 0, right? So we initialize it with the value of 0. So now it, after putting an element, it will uh, signal the semaphore, right? So now the value will become uh, 1, right? Now let's say we assume that consumer is not running, right? Or let's say the consumer is not yet scheduled for execution and producer is running continuously, right? So what will happen? It will produce another element right here. It will produce another element. Count is still not equal to buffer size, so count is 1 actually. So it will paste it in the buffer size and again signal the semaphore. So it will become 0, 1, 2, 3, 4, and so on, right? So and again your count is also incremented every time, right? So once your count becomes equal to 4, equal to 5, at that time your full cells is also equal to 5, right? So once your count is equal to buffer size, now since count their consumer is not yet running, it is not scheduled for execution. So count will stay same, which means it will stay at 5 unless consumer starts executing and it decrements, right? So what will happen is like your producer will not be able to place any more item in the buffer, right? Now on the other side, let's say now if consumer starts running, it first, this is important here, it first waits on the full cells. So which basically mean now if in this example, if now full cell is equal to 5, so now what will happen? Every time it will pick a one element from the buffer, increment the out, the index from where it is picking the element, and decrement the count, right? So what will happen is like, and then it will do the iteration again. So in every iteration, the full cell will start decrementing. So from 5, it will become 4. So at 4, and then 3, and then 2, and then 1, and then 0. But once it becomes, the value becomes negative, at that time what will happen when it will execute wait again? Once the value of this becomes negative, the consumer will be blocked. It will not be able to run. Now it will be able to run only when producer continues its execution and finally signals the full cells, right? So when it says signal full cells, then the consumer will be unblocked and able to continue its execution, right? And again, the same thing here, signal and wait, they are uh, uh, system calls, and full cell is a semaphore which is maintained at kernel level code. So this is how the things will look like. Like if you want to visualize or understand the behavior of the producer and consumer or how they are synchronized. So on the x-axis you have on x-axis you have time, and on the y-axis you have how many cells in the buffer array are full. The maximum value is buffer size, right? Like if it is 5, so the maximum values you can have is 5 cells are full, right? So here, what is happening is that number of full cells, they are increasing. How many cells are not empty? They contain a value. So they are increasing. Why they are increasing? Because your producer is continuously running. Like here, producer made multiple iterations and it started filling the array. And as a result, what happened is that your total number of items placed in the buffer, they are increasing. But at this point, until this point, your consumer didn't get a chance to run, right? So since it didn't get a chance to run, what will happen? Like there will be no reduction in the number of elements in the buffer because no element is retrieved. But once your consumer starts running, the number of elements they will reduce. And again, let's say if your producer is running again, So it will again start filling, and again the number of arrays will increase. And now let's say after this time point, let's say that uh, your producer is context switched out. So which means it's not running, or it is not scheduled for the execution, but the consumer is scheduled for execution multiple times. So what will happen is that every time if you go back to the code, so if is scheduled for execution multiple time, and while producer is not scheduled, so in every iteration it is doing what is it is doing wait operation the full cells. So it is reducing the value from 5 to 3 to 1, right? So what happens is that your number of elements in the buffer reduce, and once it reaches zero, your semaphore value reaches zero. So what happened at that time point, your consumer will sleep or it will be blocked. So this is the situation when the value of the full cell has reduced back to a negative value. At that time point, say when full cell was zero and you invoke wait one again on it, so it is decremented by one, so it becomes -1, and your consumer is blocked or put to sleep. So consumer will keep sleeping as long as it is not signaled again, and it will not be signaled again until your producer gets the chance to run again, right? Because it is the producer who during after its execution or after putting an element in the buffer invokes the signal, right? And then at that time your number of elements in the buffer again start increasing, right? And this is also an interesting case when your number of elements in the array are equal to the buffer size, then your producer stays in the while loop, right? So this is the maximum. So you can actually see it from the code here. Here, it doesn't fill the array anymore. So it will wait until the consumer again executes, and it starts retrieving the elements from the buffer array. Any questions? Okay, here is another example. Actually, it is very similar example to what we have seen in the previous producer consumer case. Suppose that we have a resource that has 5 instances, right? So our process that, again, this is an example of how we can use the semaphores, in what situations semaphores are useful for synchronizing multiple processes. So if there are, let's say there is there is a resource which has 5 instances, a process that needs that type of resource will need to use one instance, right? So we can now allow at most 5 processes concurrently using these 5 resource instances. This is different. By using the semaphore, we can allow 5 processes to run concurrently at the same time. Uh, Another process that want that resource need to be blocked. So how can we code those processes? So uh, it is just like, for example, uh, you have one producer and you have let's say 5 consumers, and assume that the size of your buffer array is 5. So let's say that first producer fills the array, so all of the elements are all of the elements contain some value, so which means the buffer array is full. Now 5 producer can run concurrently at the same time, right? Because all of them, if I take you back to the code example here, so let me discard these annotations. So for example, uh, if let's say let's simply assume that we have a single producer and we have 5 consumers, right? And also assume that producer was allowed to execute in such a way that it filled all the five buffers, right? Like I'm just putting here some tick mark to indicate that uh, these all of these arrays elements have values, right? And then your array become full, and if the value of here I'm assuming, okay, it's okay, we are saying that there are 6 elements in the buffer. But let's say that the maximum value of our semaphore is 5, right? So then if what can happen that 5 consumer processes can say at the same time wait full cells. So uh, what will happen is that 5 of them will be able to continue their execution because they will not be blocked. However, when the sixth process comes in and it wants to execute wait, now the value will be decremented from 0 to -1 and the process will be blocked. So this is different from binary semaphore or from which is basically mutex, or this is different from lock, spin lock. Remember in spin lock, what you are doing is like you are saying I can allow only one process or a one thread to enter the critical section, right? Or you want to enforce the mutual exclusion. Only one process can enter the you can enter the critical section at a time. Here, our purpose is to actually synchronize the execution of processes which need uh, a resource, but that resource has more than one copies. Like for example, as we said, 5 elements in the from the buffer can be read at the same time from 5 different consumer processes. So how to again, if you have 5 instances of a resource, and each process need one copy of that resource for its execution to continue with its execution, and if we can allow at most only 5 processes to concurrently use those resources, how can we code this example, or how we can code this problem, right? So it is straightforward. So since you have only 5 copies of the instance, and each process needs only one copy or one instance of the resource. So we can have a semaphore whose initial value is set equal to 5, and then we can organize the code of those processes as the following. At the start, we can have wait, then in the middle, they make use of the instance or of the resource, and then once they are done, they invoke the signal. So if we have this structure, then we can now ensure that we can allow 5 processes to run concurrently, each one using one instance of the resource. And if there is a sixth process, then it will be blocked. Okay. Uh, Again, remember we said that wait and signal operations, they need to be atomic, which mean that we need to make sure that only one process can execute wait at a given time, or only and same is true for the signal operation. So it's mean they need to be implemented as the critical section, right? Uh, so how can we do that? How can we implement that? So before answering that, when we are implementing the semaphore and operations of the semaphore, we need to first define a data structure. So for example, here we are defining a structure with the name of semaphore, and it has 2 data members. One is integer, and we are giving it name of value. The other is a pointer of type. Like here, we are just saying struct process type, but I mean, it can be process control block, a pointer to the process control block, right? Remember, semaphore is a kernel level data structure, so it can have the pointers of process control block type, right? So with each semaphore, we associate a wait queue. So this is basically the wait queue or the wait list. So the processes waiting for the semaphore are weighted here, or they are inserted into this list. The point, so what we do is that we simply link together the process control blocks of all the processes which are blocked on the semaphore. Okay. So uh, when we how we can now implement. So remember, when what is the share variable, like let's say if 2 processes are trying to execute the wait at the same time, what value they are going to change? They are going to change the value, the value member of the semaphore, right? And here in the first statement, you are you are actually updating the value, which is basically decrementing, and in the second statement, you are reading the value and comparing it again against zero in the body of the weight function, right? So which mean that you need to enclose these statements in a critical section, right? And how you can do that? Anyone who want to answer that? Okay, let me repeat my question. So we what we want is that uh, only one process or one thread should be able to execute the wait operation on the same semaphore, right? Why? Because uh, because otherwise we cannot achieve the semantics of the weight, where we are saying that uh, because we want to do these two things in the single step as an indivisible part. And for that we said that the variable, which is the value field of the S data structure, a semaphore data structure, it need to be protected by making it a critical section, right? Now, if we want to achieve that only one process can execute this block of code, which is shown in red, how can we do that? How can we enforce that only one process at a given time can execute this block of code? We have
Hmm.
seen at least one mechanism in previous lecture, right? Any suggestions? Okay, wrong
Probably
answers are
remembering
also
wrong, but
accepted
by checking, was it interest or whatever it was, or
by checking what?
never mind, I'm remembering it wrong.
No, okay. Say it. Don't be like reluctant. What were you
Because
saying?
wasn't there like we had the thing where it checked like if the process was interested in running, and so
That is Peterson's algorithm, right?
gotcha, and that has nothing to do with this.
Yep, yeah, but remember the problem with Peterson algorithm was that you can use it only for synchronizing two processes. And second, the problem
Ah,
with the Peterson's algorithm is that if instructions are reordered on your machine by the compiler and by your hardware, then it will not work.
right.
Yeah. So any other solution we can do to
Talking
enforce
about a binary
mutual
semaphore.
exclusion? Yeah, binary semaphore, you can use the spin lock, right?
Right.
So binary for semaphore is actually same as spin lock. So binary semaphore actually it also has its own wait and signal operation. So you need both wait and signal operation even when you are using the binary semaphore. And I'm just translating or rephrasing my question. Like if you have to implement the wait and signal operation for the binary semaphore, so then you again have to put this block, you have to treat this block as a critical section, and you need to enforce the mutual exclusion for this block, for this critical section. How will you do that? Okay, here is the hint. We covered it in the last lecture, guys. Atomic instructions? No? Okay, let me then explain. Okay, let me pick this thing and take it to week 13, day 1. Now, remember, so what we want to do is that we want to put this part, we want to treat this part as a critical section. We want to enforce mutual exclusion on that, which mean that only one process should be able to perform these statements, like decreasing the value and then testing it against zero, right? So we need to put a lock here, right? get the lock, and then once you are done, release the lock. Right? And how can you do that? By using atomic instruction. We studied two atomic instructions, compare and swap and test and set, right? So let's say I
I
want to
remember that
use
now.
compare and, sorry?
Or I was just saying, right, I remember that now. Sorry.
Yeah. So let's say we want to use compare and swap. So for compare and swap, what we do, we have a common variable, a shared variable named lock. You can have any name, but I'm, let's say, giving it name lock, right? And which is initialized to 0. Now, if there is a process, let's say there are two processes, process P0 and P1, right? And both want to invoke wait, right? Wait S. And this also want to invoke wait S. So then how I'm going to implement this wait. So before this red block, I will do what? I will do while uh, I'm just writing compare and swap CS, right? Address of this lock. If its expected value, if its current value or expected value is 0, then set it equal to 1, and then current value will be returned, right? So if it is if the current value is equal to 1, then keep looping, right? Or let's say if you want me, I can also write in a different way. If it is not equal to 0, right? So I simply put this while here at this point, right? Before the block. And after the block, after I'm like done with comparison, right? So or maybe at this point, I can release the lock, and releasing the lock is simple. You simply put lock equal to 0, right? So now let's say if process 0, both P1, process 0 and P1 both invoke wait at the same time, right? So when they enter the body of the wait, what will happen? Now, first, initially lock is 0, right? Lock is a global variable. So both after entering will try to execute the while, and inside the while they will try to execute cas, compare and swap. But compare and swap is an atomic instruction. And remember, only one process can execute atomic instruction at a time. The other will ask to wait, right? So we can select any one of them. Let's say I select P1. So P1, what will the P1 do? It will say, okay, is the current expected value equal to 0? Yes. Set it equal to 1. So it will be set equal to 1, and the old value will be returned, which is 0. So is 0 not equal to 0? This condition is false. So it will go through. Go through mean now it will be able to update the value change the value of the semaphore, right? So let's say that if the value of the semaphore was, let's say I'm saying initial value was 3, so it will be decremented to 2. And then since it is not less than 0, P1 will not be blocked, and then it will release the lock, right? But remember, P0 was asked to wait when it tried to execute the cache. But once, and so before lock was set back to 0, in meantime, if the P0 was trying to execute cache, it was getting stuck here, right? But once the lock is set back to 0 by process P1, only then the process P0 will able to go through, right? So this is how you can actually enforce the mutual exclusion on these statements, or this block of code which is uh, modifying the variable value. So this is critical section here, and this is also critical section here. So it's mean that you also need to do the same thing. But the good thing, why then you can say, okay, you can ask the question like, if we are supposed to we're supposed to put the atomic instruction like cast and swap before if we are supposed to enforce the mutual exclusion here by getting the lock at this point and then releasing the lock once we are done at this point, then what's the point of having the semaphores? We can use the locks directly. The thing is that if you want to use locks directly, they are low level. You need to write your compare and swap or test and set. But the good thing about wait and signal is that they are system calls. They are implemented as kernel code, so you don't need to worry about anything. You just need to invoke wait or the signal on the semaphore. And the second thing is good. Second good thing is like with each semaphore, you have a list of the waiting or block processes. So if a process fails to get the lock or fails to continue its execution, it doesn't occupy your core or a processor anymore because it is not doing busy waiting, it is put to sleep. So the core or processor becomes available to for other processes to do their execution. Uh, so again, emphasizing the same point that the wait and the signal operations must be atomic, and the integer value should be updated in the atomic way. Multiple processes can make calls to wait and signal simultaneously. That is allowed. They can execute. They can make the call allowed to make the call to wait at the same time. However, only one of them will be able to execute this critical section at a time, right? But no two processes can execute wait and signal critical section at the same time, right? Kernel can guarantee this by disabling interrupts in a single CPU system. So this is one option, like how you enforce mutual exclusion by if you have a single core, you can say, okay, I'm disabling the interrupt. So when you are disabling the interrupt, then other processes don't are not scheduled until the currently running process voluntarily releases the CPU, the core. The other option is that you can use the spin locks in a multiprocessor system. And this is what we did on the one node. So spin by using that compare and swap, you were actually implementing a spin lock. The process which was not able to get the lock, it will continue spinning at that while loop. Okay, what can go wrong with semaphores? Just give me 1 minute. Okay. So what can go wrong with semaphores? So again, if the person who is writing the code, the application code for synchronizing two or more than two processes or the threads, need to be very careful uh, because if you don't use the wait and the signal operations in the right order, you can end up having synchronization problems. Before explaining that, remember, where is that slide? Yeah, remember when you are synchronizing the two or more processes using semaphore or using binary semaphore or counting semaphore. So binary semaphore is also known as mutex. So you first need to put the wait statement, and then you need to put the signal statement after the critical section, right? Now, if you are doing that, if you are supposed to do that, but when you are writing the code by mistake, you change the order. So let's say you have a binary semaphore, right? And instead of when you are writing the code for your process, instead of first putting wait and before the critical section and signal after the critical section, by mistake use them in the wrong order. So now what will happen? So if this is the structure of if this is the same structure used by multiple processes who are using the mutex to enforce the mutual exclusion, now both processes, let's say P0 starts execution and P1 also start execution. So first P0 calls signal on the mutex, right? So the what is the value of the mutex? Value of the mutex is initially set equal to 0, right? So when it will call signal, it will be incremented to the value will be incremented to 1, right? So the P0 will not be blocked, it will continue its execution, right? Now when P1 will invoke also the signal, the value is already 1, so it will be clamped at 1. So when the value is clamped at 1, P1 will also, it is not negative, so P1 also be able to continue its execution, which means both will enter the critical section at the same time, which is not what we want, right? So this is like you can end up having this problem where multiple processes enter critical sections simultaneously because by mistake you used the operations on mutex in the incorrect order. You must always use wait before the critical section and then signal the mutex after completing the critical section. Second thing, another problem can be where you actually forget to put the signal and you replace the signal by wait operation. So in this case, what will happen is that a process will get blocked forever. So for example, again, if I give you the same example, let's say you have process P0, right? So uh, if the value of, let's say the value of mutex is initially set equal to 0, right? So this process will get, let's say even if it initially set equal to 1. So the first process will, when it will invoke wait, the value will be decremented from 1 to 0. So process 0 will be able to enter the critical section, but once done with the critical section, it is again executing wait, which will do what? Which will reduce the value from 0 to -1 and P0 will be blocked. Now it needs someone to signal the mutex so that it is unblocked. But again, if you are using by mistake, you are using this you didn't put here sorry, you didn't put the signal here and by mistake you place the wait at the end also. Now the other processes which are running, which have the same structure, or let's say the thread which are running the same function body, now what will happen is that another thread of process P1 which comes in and then executes wait, it also gets blocked, right? Because the value will become -2. So then all the processes will, or threads will be blocked permanently. Another scenario is like where uh, you forget to put let's say if you forget to put uh, uh, the weight or the sorry, I think this is wrong anyway, right? So the other situation is where you forget to place weight at the start, right? So if that happens, then either mutual exclusion is violated or the processes get permanently blocked. So the thing is that you always need to follow this order when you are using mutexes. You always need to follow this organization of the code. Always invoke wait before entering the critical section and then invoke the signal after once you are done with executing the critical section. Okay. The next topic which we are going to cover is monitor. Monitor is actually a high-level abstraction. It is also used for, the purpose of monitor is also to synchronize processes or threads, but it is a high-level abstraction, higher than the abstraction of semaphores. Remember, we first talked about how can we synchronize the processes, right? Then we covered the Peterson's algorithm, and then we said, okay, this algorithm works only for two processes and it doesn't work even on modern system where instruction reordering is a performance optimization, right? Then we said, okay, how can we implement the locks? And for that, we said we can use the atomic instructions. And we have seen two examples like compare and swap and test and set. But the issue with compare and swap and test and set is that yes, they work, but they are too low level, which mean like it is difficult for a programmer or person to reason about them. So that's why we talked about semaphores. So the good thing about semaphore is, and also another thing with the implementing the locks using atomic instruction is that they waste the time when they are doing busy waiting. They waste the CPU time or CPU cycles. So then we talked about semaphores. So semaphores provide two good things. One, that they don't waste the time when a process is not able to successfully get a mutex, because if it is not able to get the mutex, it is get blocked, so it doesn't infinitely execute a while loop, or it is not spinning and hence not wasting the CPU time. The other good thing is that wait and signal operations performed on mutexes are on the counting semaphores. They are system calls, which mean they are implemented by the kernel. So it is not the responsibility of the programmer or the application developer to make sure that they are implemented correctly. The only responsibility of the programmer is to make sure that they are used correctly in the correct order in their program, right? So, but the programmer can make a mistake there, right? And you like making all the time checking that they are using the mutexes in the correct order, always first putting the wait operation on a mutex and then signal operation after the critical section. Now, monitors, they provide, they release the programmer or the application developer from this burden by making it the programming more easier or less error prone, right? Because you don't need to enforce an order. It is not your responsibility to make sure that you are just like, for example, mutexes, you are using them in the correct order. So it is an even higher level abstraction than the semaphores that provides a convenient and effective mechanism for thread or process synchronization. So it is a programming language construct. So only one thread can be one thread or process may be active or executing within the monitor at a time, right? Uh, we will see how how you can like visually how you can think about a monitor in the next slide. Okay. So only one thread or a process can be active within the monitor at a time, and only that thread or a process which is allowed to enter the monitor can perform its execution. So what we do is that we put the shared variable data object in the within the monitor, and they can be accessed only within the monitor. So since all the shared data are objects, they are within the monitor, and only one process or a thread can enter a monitor at a given time, it's mean that there is no race condition because only one thread or a process is able to access them, right? So it is just like, for example, you have some shared data, for example, let's say variable count, right? So you put count in a container which you are naming as a let's say monitor, and then you allow, and let's say you have multiple processes P0, P1, P2, which are sharing this count variable, right? So, but they can access the count variable only once they are allowed to enter the monitor. And we say that only one process is allowed to enter the monitor at a time. So since only one is allowed to enter the monitor, only one can access the count at a given time, and hence there is no race condition. So other names for monitors are thread safe classes, thread safe class, thread safe object, or thread safe modules. So we define a monitor just like we define a class in a higher level language. So for those of you who have taken the course with Java programming language or object-oriented programming, so you know what is the meaning of a class and how we create a class and how we create the objects, right? So just like in class, what you do is that you have different data members, and then you have functions. All of them are encapsulated in the class, right? So then same thing we do here. We place the data and the functions which operate on the data within a monitor. So how it concept like at the higher level language or at the pseudocode level, how it looks like. So you have a monitor, right? And then you declare the share variables, the variables which are shared among multiple processes or threads, and then you define the procedures or the functions which operate on those threads. Sorry, not on threads, on on the shared data. Like for example, let's say procedure P1, it uses the shared data. Let's say shared data X, and then you have some procedure Pn, and it also uses the shared data, let's say Y, right, or X or Y, whatever. And beside that, you have the initialization code where you initialize the shared data. So this is how it looks like. So you like this oval represents the monitor, right? And within the monitor, you have shared data, and you have operations or functions which you want to which are applied on the shared data, and beside that you have the initialization code, and then all the processes which want to enter the monitor, or which want to actually use the shared data. Only one of them can enter the monitor at a given time, and all remaining they are put in an entry queue, or they are like they need to wait for their turn to enter the monitor. So since only one can enter the monitor at a given time, so there will be no race condition because only one process will be accessing the shared data at a given time. So how it looks like when you implement it. So how you can like implement the concept of monitor using semaphores. So for example, let's say if you want to use the binary semaphore or a mutex, so we initialize the mutex to a value of 1. Then each procedure is replaced. Each procedure means these procedures here. So what is the like what is the body or a function? What is the body of a let's say the procedure P1? Uh, let uh, let me rename it, not to confuse it with the process one. Let me name it as function one. So normally how a function looks like. So you have function name, and then you have some parameters, and then you have the body of the function, and in the body of the function you have some code, right? So when you implement, so this function one is actually inside the monitor, and it operates on the shared data. But when you implement the monitor using the semaphores, so using the binary semaphore or mutex, so what you do is that simply before every function in the monitor or in the monitor class, in the body, when you enter the body, you simply first get the mutex, which is wait the mutex, and then here wait the mutex, and here signal the mutex. So each procedure, its body will look like uh, this, that you initially have the mutex, you perform the wait operation on the mutex, and then uh, you execute the body, and which is actually using the shared data, and then you signal the mutex. Now it conceptually what happens is like uh, mm, let me so what will happen is, let's say if you have a monitor class, right? And it has some shared data. I'm just naming it at X and Y. And you are saying, okay, add X, XY, right? Which is, and this is your code of the function add X and Y. So it is saying, okay, X is equal to X plus Y, right? And yeah, that's it, right? So uh, what you do is like here, you simply put, sorry, not signal. You put wait mutex, and here you simply put signal mutex. Now let's say I have a process P0 and I have process P1, and globally I make an object of the monitor class. I'm naming it as, let's say, monitor M1, right? And P0 says M1 dot add XY, and P1 also says M1 dot add XY, right? Now, both of them will execute this function, but then both of within the body, they will first execute wait. And we have just seen that wait is implemented in an atomic way by using uh, by using the spin locks in the kernel level, which mean that either P0 will be able to continue, or P1 will be able to continue, right? assuming that value of mutex is initially set equal to 1. And if we let's say assume that P0 is successful, then what will happen that P0 will able to perform the operation x is equal to x plus y, but P1 will be blocked because when P0 will say wait, it will be reduce the mutex value to 0, and then when P1 will say wait, it will get blocked, right? And it will stay blocked as how long until the P0 invokes signal, right? Now here we can see that only one process is allowed to execute. So it is conceptually same as we are saying that only one process is allowed to enter the monitor at a time. Again, there are some issues with the monitor. For example, when the process P0 says signal mutex, process P1 is blocked, right? Sorry, process P1 is unblocked. But M1 process P0 itself is also executing, right? So if it starts, if it has some code here after the signal, it will continue executing that code, and P1 is also unblocked. Now we end up in a situation where both P0 and P1 are in the monitor at the same time. How can we avoid that? Possibly we will talk about that in the next lecture. Any questions? Any questions? No? Okay, so if no questions, then that's all for now, and we can meet again on Thursday. Have a
Thank
nice
you.
rest of the day. You too. Have a good day. Thank you.